Hello, my name is Hua Chen. I'm one of the Utilization Management Medical Directors, also in the Georgia Tech program. This is my project for ISyE 7406. This is going to be a project where I take a look at Medicare use and medical utilization related to costs of Medicare. All right. Let's get started. So first of all, medical spending in the United States is very high, $4.3 trillion. Currently this year, it's averaging out to $12,000 per person. Utilization management is the idea where you can try to take a look and manage the different aspects of medical spend. And by managing different aspects of medical spend, you can take a look at overall spend and control the costs of the overall spend. Machine learning is a great tool to be able to look at this because I feel like there's going to be a lot of patterns. And in this particular data set that we got from Medicare, it's a diverse data set that's based on county, state, and whole entire regions, and even the country, where each region has different types of healthcare utilization, and each of them were associated with some type of medical spend. And all this was captured into this very large data set. And as a result, I wanted to do an observational study taking a look at this data set to see if we could correlate different types of spending with lower medical spend. So we are given a very large data set, 50,000 rows, 250 columns with lots of different types of information. There was a lot of quality challenges with the data. A lot of the columns had very incomplete data. Some of the actual quality metrics that were associated with this data set were almost all empty. 48,000 of those rows were empty. The other columns did contain some utilization metrics, but when the regions went down too granular and there was not enough population, a lot of times all we got was the asterisk. So we needed to kind of clean up some of that data. And the idea is to try to use this data set to find correlations and patterns, and especially to identify ways to handle what I think is going to be the nonlinearities that can be seen within the data. So the data source link is given. My target value is actually going to be the total per capita spend per member. So the more we're spending per member, the more expensive the care is. The less we're spending, the cheaper the care is. And what I'm trying to do is figure out the utilization of these services, such as inpatient, outpatient clinic visits, skilled nursing facilities, inpatient hospital visits, rehabs, long-term care hospitals, home health services, all these different categories of spending, and find out which one of these tend to drive up the cost of medical care, which one of these drive down the cost of medical care. It's going to be split into the percentage that Medicare spends in each of these categories, and it's also going to be put into how many of the percentage of the beneficiaries are using these particular services. So after cleaning this data set, we have ended up with 20,000 rows, identified 36 medical utilization features that I wanted to look at, and that one target, the total per capita spend. All right, let me give you a visualization of this data set. So in terms of exploratory display of this data set, this is the per capita spend. This spans multiple years, multiple county regions. As you can tell, we're averaging about $10,000 per patient, when it does fall into a nice normal distribution. Already you can see on the right, there are some correlations, both positive and negative. Now let's take a look at the different features. So these features, I did a scatter plot of these features. Everything on the Y is the per capita spend, and on the X is going to be the target variable we're looking at. In this one, the first square right here is the inpatient standardized percentage spent on inpatient care. This one, the beneficiary, the percentage of patients on utilizing inpatient care. As you can tell, the more patients in the hospital, the higher the spend. Interestingly enough, the more we're spending on hospital care, it seems like there seems to be somewhat of a decrease in cost, which seems to be somewhat backwards, but maybe where we're spending no hospital care at all, these end up being spending the most because they get the sickest and end up in the hospital the most. So in this particular place, we have inpatient, observation, and emergency room visits that can be seen. In this particular slide, we have the ambulatory surgery centers, the ASCs. Then we have the skilled nursing facilities, the SNFs. and the inpatient rehabs, the IRFs. In this one, we have long-term acute care hospitals where patients go for like 6 weeks at a time, 3 months at a time, stay in the hospital. We have home health, and then we have hospice. Over here, we have office visits, we have procedures, and then we have medical tests. And I want to point out that some of these really do have nonlinear curves, like there are bends in some of these curves, there's flat areas in some of these curves, and some of these curves may even be a little U-shaped. Imaging, durable medical equipment, and outpatient dialysis. And I do want to point out the steep curve in outpatient dialysis. The more that patients are on dialysis, the more we're spending. And also, interestingly enough, if we have some outpatient dialysis, if more is being spent on outpatient dialysis, well, then it's interesting, you know, the cost of care somewhat flattens out also. Here's rural, underserved, ambulance, and Part B drugs. All right, so my proposed way of analyzing this data set, I'm going to be taking a look at statistical techniques, specifically ridge regression, linear regression, and polynomial regression. Those are known to be more interpretable, especially for overall gestalt. And secondly, I'm going to be taking a look at non-parametric methods that are able to handle nonlinearities, specifically the KNN nearest neighbors algorithm, and then starting to be into the more advanced machine learning algorithms, such as the ensemble learning, random forest, and the boosting tree algorithms, specifically XGBoost, well known for its performance in some of these aspects. Lastly, I'm going to be taking a look at features as I take a look at these different algorithms and trying to figure out how can we figure out which features are influencing the amount of money spent on the care. And lastly, I'm going to do some perturbation analysis where take a look at one data point and then put what if scenarios. What if different categories of spending were different? How much would that change my medical care spend by? All right, so first of all, let's take a look at ridge regression. Ridge regression separates out into variables that are well known to add and variables that are not known to add. Interestingly enough, the number of beneficiaries on outpatient dialysis is steeply related to the amount of spend. We saw that previously. As pointed out in this one, we're able to get directions of spend. Certain things increase spending, certain things decrease spending. Per the ridge regression, the outpatient dialysis amount being paid for outpatient dialysis seems to be correlated with some type of negative spend. Perhaps these two facets somehow are related. If there's a lot of patients that should be on dialysis, but they're not getting outpatient dialysis, that means they're getting inpatient dialysis, and the care could be very steep for those particular patients. All right, so let's take a look at the ridge regression results. Here we have the actual value. These are all different types of the values that we've got normalized, and these are the predicted values that we had. And you can tell we are able to make decent predictions. And mean squared error is near 0.1, and mean absolute error is near 0.2. Here's my linear regression results. This is very similar to the ridge regression results. We didn't get that much benefits by tossing out some of the variables and features. I tried to use a more complicated algorithm, the polynomial features, thinking that there's maybe some nonlinearities. I chose a third degree because most of them seem to be not U-shaped in origin, and I did get worse results. KNN algorithm is a first non-parametric, that's able to handle nonlinearity, and my results did improve. My mean squared error did decrease. When I went to my random forest, this is where I started getting much more improvements in my performance. Interestingly enough, when I look at the feature importance of random forest, the first one that pops up is not outpatient dialysis beneficiaries, even though it is up there, but it is rather the amount of patients utilizing home health services. My random forest regression results, as I mentioned, it's 0.109. This is very similar to the linear regression results. This is for 5,000 trees. And this 5,000 trees was obtained by parameter tuning. However, when I went to the boosted trees, the XGBoost algorithm, the performance was much better. And again, interestingly enough, the features that it selected as important were again different than the other two. In this one, the boosted tree seems to make the most intuitive sense. The amount of patients, the amount of patients getting inpatient services, the amount spent on inpatient care, it seems to be highly significant in trying to determine the per capita cost of care. And the way this thing ranked seems to make a lot of intuitive sense. Inpatient care, ER visits, the number of outpatient services, the number of skilled nursing facilities, Part B drugs, these are all known to contribute heavily to the cost of Medicare. And down here are less things that contribute to the cost of service. Amount of patients in long-term acute care, we tend to only spend one amount for those, so this doesn't seem to influence the amount of care as much. And in the boosted tree regression results, I want you to take a look. My results are much better. The MSE is significantly lower, nearly half of that for linear regression, and so is my mean absolute error, and my R squared also increases dramatically. In order to double check these accuracies, I double checked it with some cross-validation. Because of computational intensity of some of these algorithms, I had to select a subset. So I chose linear regression, KNN, and XGBoost. Doing it over 5 validation splits, it's still noticeable. XGBoost is the clear winner. Then I did some initial experiments in perturbation. What I did was I perturbed some of these. I picked one select point, my first testing point, and said, okay, after getting my testing point, I want to perturb these different categories around to see if it leads to different types of decreases in overall spend. Interestingly enough, by changing things by 1%, I am able to get decreased utilization in certain things. For instance, if I increase the DME spend, I'm able to decrease my overall spend by 0.2%. And this seems to be true throughout. There are different things that you can decrease and increase, and you can get different types of percentage spreads across everything. All right. So my discussion and conclusion. First of all, linear regression and its cousins can really help to take a look at the larger picture. By looking at the overall cluster, the overall, the overall spots on the graphs, you're able to see that there is correlation, and linear regression really gives you a good idea of what things tend to drive up costs and what things tend to drive down costs. But interesting enough, even though the non-parametric regressions and specifically XGBoost are much less interpretable, but at a very localized region, they give you pretty decent prediction. And by using things such as perturbations, you can guess how you can try to decrease utilization in that particular area. Like for instance, in that particular choice that I chose for that medical space, by changing the DME value, you seem to be able to change the total spend by the most. And so as the organization, you may say, how do we try to get providers to consider the use of braces or other DME instead of procedures or hospital stays? Now, again, this microanalysis may be more useful at the regional level, but again, causality does not equal correlation, and we want causality. So this means that this possibly opens up new A/B testing and controlled experimentation. Here's my appendixes, links to files, links to codes, links to data. And here's my bibliography and credits. Right, thank you so much.